And we're back at it again. So remember, we're really just going to be looking at two different things today. Mainly, we're going to cover the assumptions and conditions that go with the central limit theorem. And second off, we're going to do an actual example that kind of works with the mean type situations where we're dealing with quantitative data instead of categorical. So we're going to break this down into two chunks. First, let's go ahead and look at the slides. All right, so the central limit theorem. This is where we kind of ended in lesson 8, and we'll pick up here. So remember, central limit theorem, essentially we just said, hey, if you know the mean, the standard deviation of a whole population, then when you take samples from that population, then the distribution of those samples will be the normal curve, all right? So let's talk about when this works, how we know it works. There's two major times it works. We already went through these with proportion, and you're going to notice that it's going to be essentially the same. But if you remember, some of our conditions when we were doing it with proportions were things that involved the use of P and Q, like P times N and Q times N both need to be bigger than 10. So we won't be able to have those for conditions anymore. So we will have some new ones that will kind of replace those. But essentially, we're going for the same thing here. We want to make sure that the independence assumption is met and that the sample size assumption is met. Now remember, just like before, assumptions are really hard to prove. So instead, we kind of focus on smaller conditions that help us understand the bigger assumptions. All right. So what are the conditionals for quantitative type questions? First off, to get the independence, it needs to be a random sample. So this is the same as before. It's called the randomization condition. The data values must be sampled randomly. Now, 95% of the time, what this looks like is the question will say, we got a random sample of 20 people, or we got a random sample of 150 people, or a random sample of 200, or we went out and found 20 women randomly. That's all it needs to say. That means they randomly found them. Great, cool, awesome condition. Check. All right. 10% condition. When the sample is drawn without replacement, the sample size n should be no larger than 10% of the whole population. Again, when you're dealing with really small populations, this one kind of matters more. But when you're dealing with like thousands and thousands of people, you probably will never reach 10% of them in one individual sample. So this one's pretty easy to meet as well when we're dealing with larger populations. Now, the last one's kind of new. It says the large enough sample condition. It says the central limit theorem doesn't tell us how large a sample we need. For now, you need to think about your sample size in context of what you know about the population. So this one's really odd because basically you want a sample size that is large enough that your standard deviation is going to get small. In other words, you don't want this huge range of numbers to be your sampling distribution because then it's useless in terms of using it for questions later. All right. We'll talk a little bit more about that as we go. So what does the central limit theorem say about sampling distributions of any mean or proportion? It says that it is approximately normal. All right, so nothing fancy there. We already have mentioned that like 100 times, but which normal model? All right, so remember, whenever we deal with a normal model, there are two things we need. We need to know what the mean is, and we need to know what the standard deviation is. Now, we have already covered that with proportions. We're going to go ahead and take a look at that with the average situation today, all right? But it says, remember, if these are the two things we need to find, for proportions, the mean is centered at the population proportion. And for the questions we're looking at today, it's centered at the population mean. So what about the standard deviations? Well, we have a formula. The new standard deviation for the sampling distribution of a quantitative situation, the new standard deviation is the old standard deviation. That's what this guy is. All right. The old standard deviation divided by the square root of the sample size. Now, this should look very familiar because for the proportion question, it was the square root of p times q divided by the square root of n. Now it's the standard deviation divided by the square root of n. So it's still got that square root of n, all right? So this will be the formula you use for your standard deviation, all right? So that's the formula you use for the new sampling distribution standard deviation, All right. So it says here that the standard deviation of sampling distribution declines only with the square root of the sample size. Therefore, variability decreases as the sample size increases. While we'd like to take a larger sample, the square root limits how much we can make a difference. It is called the law of diminishing returns. This slide's weird and kind of gives you information that's a little bit challenging to understand, so I'm going to explain it to you right now. Essentially, it's saying this. We don't want our variation or our standard deviation to be very large. The reason why is we want to use this to kind of pinpoint how accurate our sample is. And if our standard deviation is huge, then it gives huge leeway for the averages of your sample. If I wanted to know the average, I don't know, percent of students that are going to graduate, I don't want to go into Dr. Blair's office and say, well, we'll have anywhere from 20 to 90% of our students graduate. That's not going to be a good enough response for him. He wants that to be a much more narrow, maybe like an 80 to 85% chance that they're going to graduate. So, in order to get that smaller, there's only one thing in both formulas that could make it smaller, and that's when we divide by n. So, obviously, if you divide something by 2, let's say I have 10 slices of pizza and I divide it by 2, all right, then that means everyone would get, or well, everyone being the 2 people, would get 5 slices. All right. But if I up that bottom number to 5, so that means I'm going to say, hey, I'm dividing by 5 instead of 2. Now everyone only gets 2 pieces. In other words, when you divide by a larger number, it makes your overall answer smaller and smaller and smaller. So what this slide is saying is that the only way that you can kind of lower that variation, kind of shove everything towards the middle of your normal curve, would be if you can raise the sample size. All right. Now, the problem with this is it's the square root of n, which means that at some point, it doesn't matter how big you make the sample, it's not going to lower the variation in any way. That may seem weird, so I'm going to use this graph to kind of help you guys understand. This is the graph of 50 divided by the square root of x. In this case, x is our n, all right? So if I wanted to lower my variation to get a standard deviation, I do my whatever work at the top, all right? So in this case, maybe our original standard deviation was 50. So the new standard deviation would be 50 divided by the square root of our sample size. Now, if I only got one person here, all right, one person, then that means that I would expect my new standard deviation to still be super huge, around like 40 to 50 range, all right? But the moment I jump it up to, I don't know, let's say halfway, 5, all right? At 5, we're looking more at this like 22, 23 range, all right? So that means just by moving it up 1 or 2 or 2.5, by changing the x, by increasing it by 2.5, we've already lowered the overall standard deviation by a ton, all right? But as you notice, this curve kind of starts leveling out, meaning that the difference between having a sample size of 20, which would be right here, and a sample size of 40 is only the matter of moving like 4 in terms of your overall standard deviation. So at the beginning, it makes a huge difference. So small sample sizes are not good, but the moment we start raising the sample size, it kind of quickly makes our variation drop extremely, but then it kind of levels out and it doesn't make as big of a deal. That's what it means by the law of diminishing returns. It means that our sample size, as we increase it, it will make our variation go down. But at some point, it really doesn't go down much further. All right. Cool. So that's kind of some of the conditions and theory behind what's going on. Now we're going to go ahead and take the rest of this time to look at an example question. All right, so let's go ahead and take a look at this question. A college physical education department asked a random sample of 200 females to self-report their height and weights, but a percentage of students with body mass indexes over 25 seems suspiciously low. One possible explanation may be that the respondents shaded their weights down a bit. The CDC reports that the mean weight of an 18-year-old woman is 143.74 pounds, with a standard deviation of 51.54 pounds. But these 200 randomly selected women reported a mean weight of only 140 pounds. Based on the Central Limit Theorem and the 68, 95, 99.7 rule, does the mean weight in this sample seem exceptionally low, or might this just be a random sample to sample variation? So what is this saying? It's saying, hey, look, our sample ended up having a low body mass index. Maybe it's due to the fact that they're sharing their weights to be lower than what they should. So now instead of looking what proportion of them are over the BMI of 25, we're now looking at their actual weight, just the weight. So they're checking out of their weight what was the average. So the mean weight for this 200 women is 140, but the population mean is 143.74 pounds. So they're wondering, is 140 being the average of these 200 far enough away from that 143 that we should be concerned that it is lower than what it should be? All right. So let's go ahead and break this down. Remember, before we do anything with this question, it's always a good idea to check your conditions. All right. So we're going to go ahead and go through the three conditions that we have discussed thus far. First off, randomization condition. Does it say anywhere in here that this is a random sample? Yes, it does. It says 200 randomly selected women, which means our randomization condition is met. That's supposed to be a check mark. It just got a little ugly. Next is the 10% condition. So remember, 10% condition means that our sample size can't be more than 10% of the whole population. We are dealing with 200 female students. All right. Is 200 more than 10% of all female students? Well, 200 would be 10% of 2,000. Are there more than 2,000 18-year-old female students out there? Yes, yes, a whole lot more. So this will not break the 10% condition, so we are good here as well. Now, the large enough sample. Do we think a sample size of 200 is wrong? Well, looking at that curve we just saw, we saw like anywhere from like 0 to 10 sample size made a huge difference. But after a sample size of like 30 or higher, really there wasn't that much of a change. So is 200 going to be a big enough sample? Yes, 200 is going to be perfectly fine. It's well above 30, which is kind of your rule of thumb for most things. And we don't have to worry about taking small samples here because we're looking at 200 randomly selected women. Cool. So let's move on to actually doing the question. Now that the conditions are met, we can say, yeah, cool, let's move along. So it says, first off, remember, our whole goal here is going to be to see if this is outside the norm of our sampling distribution. But in order to look at that, we need to first know the mean and standard deviation of the sampling distribution. Now, notice here I have the little mu sign we're used to with a little y bar. And right here it has the standard deviation with a little y bar as well. This sometimes is also written like this, where it has the standard deviation sign with a little X or Y bar down here. Why do they use this as the symbols for the mean and standard deviation of a sampling distribution? Because think about what we're doing here. In a sampling distribution, we collect a whole bunch of means of samples, and then what we're doing is we're essentially finding the mean and standard deviation of those means. Well, what does X bar or Y bar or anything like that mean? It means the mean of a sample. All right, so the mean of a sample. So when we look at this up here, what is this saying as a symbol? It's saying that we want to find the mean of the sample means or the standard deviation of the sample means. So this is sometimes a symbol that they will use for the mean and standard deviation of a sampling distribution. Don't let that throw you off. Now, in this case, remember there are two things that you kind of need to separate. You need to separate the information that went with the population and the information that went with your individual sample. All right. So why don't we go ahead and underline in blue the stuff for the population? It said that the CDC reports that the mean weight of women is 143 pounds with a standard deviation of 51.54. And our random sample, let's do the sample stuff in green, is 200 randomly selected women, which will be our N, and they have a mean weight of 140 pounds. All right. So it's important to differentiate the difference between our 140, which is the mean of our sample, and the 143, which is the mean of the population. Because once we get to these two formulas down here, we want to make sure we are sticking with the mean of the population as the mean of our sampling distribution. We'll use the 140 later when we want to see if it's abnormal. So 143 0.74 is the mean of our population, all right? And the standard deviation, we actually have to do some work. So we're going to take the standard deviation, which is 51.54, divided by the square root of our sample size. Now, what was our sample size in this case? Remember, we underlined it in green already. That's going to be our 200. Okay, so what is that all equal to? Well, I'll give you a second to try to plug it into your calculator. 51.54 divided by the square root of 200. Once we plug that all in, you should be getting 3.64443. So hopefully that is what you guys got in your calculators as well. And once we have those two numbers, the mean and standard deviation, really at that point, we're ready to answer this question. So is the 140 abnormal? Well, remember, we have multiple ways of doing this. The easiest one is to see if it falls within two standard deviations. Sometimes it might even be a little quicker just to come up with a z-score so we know exactly how many standard deviations away it is. All right. We also can do our normal CDF to find out the actual percent chance of being less than being 140 or less. Let's go ahead with this one and just do the z-score one. So remember, what is our z-score one? That's when we just take the mean of our sample, which in this case is 140, and we want to subtract off the mean of our sampling distribution, which is the mean of the population. So that's our 143.74. And we want to divide that by the standard deviation of the sampling distribution. So we don't want to use the 51.54. We want to use this guy. So we're going to divide that by the 3.64443. All right. Now, if we do that, we end up getting negative 1.03. Now, in your calculator, you're actually going to get negative 1.02622, but I'm just going around, that's negative 1.03. And this is going to help us end up answering the final question for this situation. So here's the question again. It says, is this exceptionally low? Use the 68, 95, 99.7 rule. So in other words, like, is it outside of these ranges? Well, it is outside of one standard deviation, but really it's just hardly less than one standard deviation away. So 1.03. So it's one standard deviation and a little bit more away from the middle. So if this were the normal curve, all right, and we have the mean here, this guy's really only going to fall like right here, which isn't that unusual. So we could probably say, no, it's not really that unusual. This may just be sample to sample variation. All right. So again, this is an example of how to do the same type of question we did with proportions, but we just did it now instead with our mean and standard deviation of a quantitative variable. All right. So I hope this helped you guys. I'll just give you one or two questions tonight. It's probably going to focus along the lines of find the new sampling distribution mean and standard deviation of this situation, and tell me if it's unusual. The exact same type of thing you're doing here. If I add in anything else, it'll just be like a, hey, check the conditions of this. See if you guys are doing well with the checking of conditions or not. Cool, great, awesome. Well, in that case, I hope you guys are doing well. I hope you guys stay fit, stay healthy, and have a wonderful week.